This is the Solom update for March 10th, 2016. Yesterday I started checking out the board after I got all the parts down. The real-time clock worked, the temperature sensor worked, the I/O port worked, the LEDs worked, the radio worked, the power supply worked, and the battery charger worked. That's all great. Nothing from the A to D. That's not surprising. That's the finest pitch part on the board. 28 pins, and there are solder bridges all over the place, so I didn't worry about that. I had an eye exam yesterday afternoon, and so after that I really couldn't see very well. After the dilate your eyes. So I took yesterday evening off, came in this morning and started working on the A to D converter, removed all those bridges, got it functional. Voltages looked great, very clean. The current sensor was pegged at the rail. So I went in and I looked at the schematic and I looked at some other voltages. I did some debugging, and remember on if you paid attention during some of these videos, I talk about me rewiring the analog circuitry, and I redid the current side. And when I did that, I ended up swapping some op amps around in these dual op amps. And I got one of them in backwards. And I could kick myself for this. I had this one here. This is the solid key for the analog filter that goes on the current sensor. I had the plus and minus on this op amp flipped. So it was getting positive feedback, and it was oscillating like crazy. And that was actually leading to an excessive current draw. Once I figured that out, I went into this area on the board. This is that chip. This guy right here. Get this right in the middle. I ended up cutting a trace right here, and I cut this trace down here. It was fairly easy fix, and I just introduced another solder bridge to make this connection between these two pins, and I just hardwired this one across. And that op amp started singing his song, and it was great news. Everything started working. I connected up my power supply here, and I was running about 8¼ amps through that sense resistor. A sense resistor is 2 milliohms. And then I have a 60-volt power supply hooked onto the voltage, the voltmeter. All right, then I went in and I modified the routine to see how fast I could take these data samples. And I'm able to take 250 in 21.5 milliseconds or something. That works out to be about 11 kilosamples per second, which is far in excess of really what I want to do. I really only need to do maybe 1.5 kilohertz, kilosamples per second. So that's looking pretty good there. I know you're all dying to know, is it any better than it was last time? Yes, it is. Here's some of the data coming out of this. I ended up taking bursts of data, so 250 samples, and I wait a second. 250 samples, and I wait a second. 250 samples, and I wait a second. I did that for, if you look at this thing, I got 5,400 data samples. This plot here is all the data samples plotted over that time frame. So you can look, they're kind of grouped here. They're kind of bound by 24,610 to 24,640. That's 30 LSBs. At 8 amps, I have the ammeter set scaling so that I'm kind of high on the A to D input. It's the full scale on that guy's about 2.1 volts, so I'm sitting right around 1.8 or something like that. You can see that I'm pretty bound in here. It does look kind of noisy, but in actuality, it's not. 30 LSBs out of on a 15-bit A to D converter. It's 15 bits because remember, it's really a 16-bit A to D converter, but it's differential, and I'm ground referenced here, so I can only really use 15 bits of that. So 30 LSBs out of 15 bits is actually really small. If I look at that, it works out to be about 0.20%, which is awesome. It's just great. I calculated the mean here, and then I calculated the standard deviation. It's 5.6 5.6 LSBs. So that's good. The voltage, now this noise comes because I have amplifiers built in. You know, I get a gain of, I don't remember what the gain is, maybe 100. So I'm going to get a little bit of noise. It's a matter of how much is there, and this is awesome performance right here. On the voltage side, I can do something a little bit more simpler and not have any amplifiers in there, or not have any gain stages, because it's just a straight voltage divider. And this guy over here really sees on average about 2 lsb of noise, and that's freaking awesome there. That one, great. That's great. So I sent this down to Jim Kerman's this evening, and we'll go into what he found a little bit later. I got some email from the DOE. They did release the announcement for the call for proposals for round 2 of their voucher program. But that's due on April 10th. So I'm going to send that in. And Jim Kermans at CFV also emailed me the PDF of the award winners for round 1. There were 2 solar projects in that round. So it looks, the odds are looking pretty good. And at this point when I submit, I will have a working prototype. It will be installed somewhere. I'm a lot further along. It's not all vaporware when I write my second proposal. All right. This is all great news. I let that thing run all afternoon. I got a lot of data, blah, blah, blah. 11 o'clock, a new toy hit the lab here. A toy. A new tool hit the lab. I bought this thing here. This is a 3D printer, of course. It's a clone of a replicator. Dual head. It has dual head extrusion, so I can do 2 different colors. Or what is that stuff called? So there's water soluble support material. Here I'm printing out some parts on it. It's all looking pretty good. This is the exact same printer I've used before, so the ramp up time to learn how to use this was 0. I just turned it on, I built it, took a couple hours this afternoon, I got it going. So while that was doing its thing, I emailed this spreadsheet over to Jim Kermans at CFV, and I said, hey, run your little analysis magic on this, and kind of tell me where we're looking. So he did that, and this is what he found. He found that my voltage noise is what is that, 0.002% RMS, which is, it's great because you got to see that in that graph before. And the noise on the current is down at what is that, a tenth of, well, it's probably a 15th of a percent. No, I don't know what that is. A 20th of a percent. Which is kind of what I was saying we're looking at. That's great as well. His comment is it's pretty quiet. Okay, the last thing I'm going to work on this evening was I fired up FreeCAD and I drew out this little. It's kind of late. I'm losing it. What's that stuff called? Tape. The surface mount parts come on a reel of tape. And this little thing here is going to be a holder. Not that one. That's the first one I did. Here's the better one. So I can slide the tape in here, and what I'm going to do is I'm going to actually try to do a rudimentary pick and place machine. No feeders or anything, but so this is going to sit on the edge of the board. I have a vacuum pump and an air valve, and I'm going to hook it up to one of my extra syringes and actually try pulling some parts out and putting them on the board. So I printed some of these on my printer. This is the first real part that came off my printer today. So we just put them in like this. I ran them on this kind of orientation because the parts will sit this way. So this is for the rotation of the part on the board. So I have 0 and 180 out of one of these bins, one of these rows, and the other row will be the 90 and 270 oriented parts. I'll let you know how that goes. Kind of optimistic about that, but we'll see how that works out. Is there anything else? Oh, there I am at the end. No, I think that's it. Tomorrow I'm going to continue my work here, and we will see what happens. I'm going to build up board number 2, and we're going to get that running. This is a Solemn update for March the 10th, 2016. Thanks for watching.